All right, let's jump straight in. You're interested in staying ahead in the whirlwind world of machine learning, and today we've got a fascinating piece of research on our radar.
Yeah. What are we looking at?
It tackles a real bottleneck. How do we teach these massive language models, LLMs, to do lots of different things well?
Oh, okay. Without them getting confused or like needing a supercomputer just to run them, right?
Exactly. The more we rely on these large language models, the more we need them to be adaptable.
Sure. But as you know, training them for every single task from scratch is just, well, it's not feasible.
Right. And even when we try to teach them multiple skills, we often see this frustrating issue where learning one thing makes them worse at another.
Yeah, that cross-skill interference, it's a known problem. The researchers are looking at that specifically.
They are. And that brings us to the paper we've been digging into. Compositional subspace representation fine-tuning for adaptive large language models.
Okay, bit of a mouthful.
Yeah, it is. But the core idea seems incredibly promising. The authors are proposing a new way to adapt these LLMs for a bunch of different skills.
And the hook is?
They're claiming they can do it super efficiently, like even beating some of the big players on a key benchmark while using a tiny, tiny fraction of the usual computing power.
Okay, that's definitely interesting. What's the approach? How are they doing it?
Well, what's particularly exciting, I think, for people following this field is their fundamental approach. Instead of tinkering with the core engine of these models, the main weights.
Right, the bulk of the parameters.
Yeah, they're focusing on fine-tuning very specific, almost hidden areas related to different skills, these hidden state representations.
Representation editing, okay.
And then they've designed this clever little system, they call it a router, to decide which of these specialized areas to activate when it sees a new task.
So like having a set of specialized tools for different jobs.
Exactly. And a very efficient foreman who knows exactly which tool to hand to the worker. That's a good analogy.
Okay, interesting. So let's unpack this CSRFT thing.
Right. So this paper, at its heart, is all about making large language models more versatile without, breaking the bank computationally or seeing their existing abilities degrade.
And this compositional subspace representation, fine-tuning CSRFT, is the key. It stops that problem of one skill messing up another.
That's the claim. It achieves this by learning multiple highly specialized modifications within the model's internal representations, those hidden states we mentioned.
Okay, so each modification is like a training session for a specific skill.
Sort of. And the crucial part is that these training sessions happen in their own separate, mathematically distinct orthonormal subspaces.
Orthonormal, okay, sounds technical. What does that actually mean for the model?
Well, maybe you can explain that better.
Sure. In simple terms, it means these specialized areas inside the model are kept independent and mathematically well-behaved. Orthogonal basically means they're at right angles to each other.
So changes in one don't bleed into another.
Exactly. They don't interfere. And normal, in this context, just means they're scaled properly. So by making these learning spaces orthonormal, the paper argues the skills learned stay nicely isolated.
Like organizing your tools in separate drawers, so you don't grab a wrench when you need a screwdriver.
Precisely. It dramatically reduces that interference problem.
Okay, so the model has these separate, clean learning zones for each skill. But how does it know which zone to access for a given instruction?
That's the job of the lightweight router. This is a small, very efficient part of the system.
Right.
It looks at the input you provide and dynamically figures out which specialized skill areas to activate.
Yeah.
And even, how much to activate them.
Like a smart switchboard.
Yeah, exactly like that. Directing the information flow to the right expertise. It can even decide to use a combination of skills if the request is complex.
That sounds incredibly efficient. So instead of broadly adjusting the entire massive model, CSRFT makes these very precise tweaks in specific representational areas and has this intelligent router to turn them on and off as needed.
Exactly.
And the claim is this uses far fewer parameters and gets better results.
That's the compelling part. Their results on the AlpacaEval benchmark look really strong. Their LLaMA 2.7b model, adapted with CSRFT, actually performed better in head-to-head comparisons than much larger models.
Like GPT 3.5 Turbo?
Yep, and LLaMA 2.13b as well. And it did this using less than 0.01% of the parameters of the original LLaMA 2.7b.
Wow, less than 0.01%. That's
Yeah.
staggering efficiency.
It really is. It suggests the potential to get top-tier performance with drastically reduced computational costs.
Okay, let's dig a bit deeper into the paper itself. How do they structure their argument?
Well, they start by setting the scene, right, highlighting the crucial role of LLMs, but also the significant computational cost of adapting them.
A standard problem statement.
Right. Then they introduce parameter-efficient fine-tuning, PEF, as a way to tackle those costs. They mention methods like LoRa, which updates only a small fraction of the model's weights.
But they point out that even PEFT methods like LoRa are still mostly about modifying the weights, right?
Exactly. And that sets the stage for their argument that directly manipulating the internal representations, those hidden states, can be even more efficient.
Okay.
They discuss existing representation editing techniques, like the original ResFT method, but they also highlight a key limitation.
Which is?
These methods often struggle when you try to teach a model multiple skills at once, because the changes for one skill can mess up others.
The interference problem again.
Yep. Which brings them to the central problem they're tackling, this cross-task interference and the lack, they argue, of representation-based methods that effectively use principles like orthogonality to solve it.
So CSRFT is positioned as the solution, combining efficient representation editing with that mathematical rigor of orthogonality to keep skills separate. What do they list as their main contributions?
Okay, first, learning these distinct low-rank transformations for each skill. Because they operate in orthonormal subspaces, they inherently avoid conflicts.
And use fewer parameters. They highlight a big reduction compared to LoRa, right?
They do, something like 12.7 times fewer parameters. Then second, they emphasize the lightweight router that intelligently activates these specialized areas.
Makes sense.
Third, they stress that applying these orthonormal constraints directly in the hidden state space is key. They argue it's more effective for isolating skills than applying similar constraints to the model's weight matrices.
Interesting distinction.
And finally, of course, they present those impressive performance results on AlpacaEval.
Okay. How does this fit into the broader research landscape? What's the related work section look like?
They give a good overview of PFT techniques, grouping them into weight modification methods like LoRa and representation editing methods.
Right.
They acknowledge the progress these methods made in reducing overhead, but keep underscoring that challenge of handling multiple tasks simultaneously because of interference.
And specifically for multitask learning.
They discuss different strategies people have tried, like sharing all parameters across tasks.
Which risks interference.
Exactly. Or having completely separate modules for each task.
Which gets parameter heavy and inefficient.
Right. They also mention dynamic routing systems that try to activate different parts of a model selectively, but note these can add complexity.
So they position CSRFT as different.
Yeah. They acknowledge some recent work combining orthogonality with multitask learning, but point out that work mostly focused on weight-based modules. CSRFT's distinction is applying these orthonormal constraints at the representation level in the hidden states.
Got it. Now let's get into the nitty-gritty. How does CSRFT actually work? The method itself.
Okay, the core idea, like we touched on, is learning these small focused adjustments, these low-rank subspace interventions, and using that router to decide which ones to apply based on the input.
So for a frozen base model.
Right, the base model M is frozen. CSRFT learns a set of task-specific subspace transformation, A01 and AWare.
And each transformation AGI is basically for one skill.
Ideally, yeah. Each one modifies a small R-dimensional slice of the hidden state vector. It uses an orthonormal matrix, RE, and some trainable parameters, we, by, to define this change.
And that orthonormality is what keeps them separate.
Exactly. It ensures the learned directions for each task are distinct, creating these isolated pockets of expertise.
And the router, how does that work?
It takes the input embedding, X, and maps it to a gating vector, alpha. This alpha vector has values between 0 and 1 for each of the K skills.
Okay, so it decides how much on each skill should be.
Pretty much. It can use discrete gating, like an on-off switch, using a threshold like 0.5, or soft gating, allowing fractional activation. The final hidden state is the original state plus a weighted sum of the transformations, where the weights are given by alpha.
Plus IU re plus by ORU, that formula.
That's the one. And the router itself is designed to be tiny, maybe just a couple of layers, so minimal parameter overhead. It's trained jointly with the subspace transformations.
So the model learns which skills are relevant for which inputs.
Yes, implicitly. The training objective is just to minimize the task loss across all tasks, potentially with a small nudge to keep the router output sparse, encouraging it to only activate necessary skills.
And crucially, only the subspace parameters, W, B, R, and the router parameters are updated.
Correct. The base LLM stays frozen. This targeted training, plus the orthonormal separation, is how CSRFT prevents interference and stays so parameter efficient.
And the authors highlight benefits like compositional synergy, too.
Yeah, because the router can activate multiple subspaces, the model can potentially handle complex prompts that need a combination of skills.
Okay, that covers the method. The experiments seem crucial here. Tell us about the setup.
They used AlpacaEval, as we mentioned. The benchmark compares model outputs against reference responses for instruction following tasks.
And the base model was LLaMA 2.7b.
Yep. They compared CSRFT against other PFT methods like LoRa, RED, DREFT, DeLoREFT, and also against bigger models, GPT-3.5 Turbo and LLaMA 2.13b.
Main metrics were win rate and parameter efficiency.
Correct. For implementation, they learned 4 distinct low-rank transformations, using the RFT mechanism as the base intervention.
Only 4. For all the skills on AlpacaEval.
Seems so. And the router was a simple 2-layer network processing the embedding of the first token. argjuchi2 with ReLU, then MADSR4 with sigmoid, and a 0.5 threshold for activation. Tiny.
And the results, we touched on them, but let's recap.
Pretty striking. CSRFT hit a 93.94% win rate.
Which was higher than GPT 3.5 Turbo's 86.30% and LLaMA 2.13b's 81.0%.
Yes. And it also beat LoRa, which got 81.48%, and the other RevFT variants that were in the 81-85% range.
And the parameter count again?
CSRFT used just 0.0098% of parameters. Compare that to LoRa's 0.1245%, or even the base RevFT methods around 0.00039%.
Exactly. It really highlights how effective combining these specialized subspaces with dynamic routing seems to be. Okay, so the paper concludes by emphasizing CSRFT's advantages for cross-task interference using these separate subspaces and the router. What about future work?
They mention a couple of key things. One is scalability, how to handle potentially hundreds or thousands of skills efficiently, maybe merging or sharing related subspaces.
That makes sense.
The other big one is interpretability, really understanding why the router activates certain skills for a given input.
Which is crucial for trust and debugging, right?
Absolutely. They see the success of CSRFT pointing towards more multi-module compositional approaches for flexible and efficient LLM adaptation.
Okay, this is a good point to step back and look at the historical context. This CSRFT didn't just appear out of thin air, did it?
No, definitely not. The whole journey really started because fully fine-tuning these huge LLMs became impractical.
Too costly, too much data needed.
Exactly. That spurred the whole field of parameter-efficient fine-tuning, PEFT. Early ideas involved adding small adapter layers or just tweaking tiny parts of the network, like bias terms.
Right, and then things like prefix tuning came along.
Yeah, optimizing continuous prompts to guide the model. But LoRa was a really significant step in PEFT, wasn't it?
Absolutely. Low-rank adaptation. It showed you could decompose the weight updates into much smaller matrices and still get great performance with way fewer parameters.
But critically, most of these methods, including LoRa, were still fundamentally about changing the weights, the core connections in the network.
Which is where the idea of representation learning, or representation editing, comes in, trying to directly influence the model's internal understanding.
Precisely. Methods like the original RevFT explored directly editing those hidden state representations. They offered potentially even lower parameter counts.
But ran into that multitask problem.
Yeah. When you try to adapt a single global representation for many different skills, you hit catastrophic forgetting losing old skills or negative transfer where learning skill A hurts skill B.
What CSRFT calls cross-skill interference.
Right. That was the key obstacle these representation editing methods faced in multitask scenarios.
And the idea of using orthogonality wasn't entirely new, but CSRFT applied it differently.
Exactly. People had explored orthogonal constraints for weight modifications, maybe in some LoRa variants, to try and keep different adaptations separate.
Okay.
The big innovation in CSRFT is taking that principal orthonormal constraints and applying it directly to the hidden state representations, creating those isolated knowledge pockets within the activations themselves.
So CSRFT is really a synthesis, combining efficient representation editing with dynamic routing and this novel application of orthonormality in the hidden state.
I think that's a great way to put it. It's designed specifically to overcome the limitations previous approaches had with multitask adaptation.
Okay, so boiling it all down, the core takeaways are CSRFT offers a way to adapt massive LLMs for many tasks using dramatically fewer parameters.
Orders of magnitude less than full fine-tuning and even significantly less than methods like LoRa.
And in tests, it even outperformed much larger models. The key is isolating skills in these distinct orthonormal subspaces within the hidden states.
Right. And using that lightweight router to intelligently activate and compose them based on the input.
This representation-based approach seems better at preventing that cross-task interference than weight-based methods.
The results suggest so. And the strong performance on AlpacaEval points to real practical advantages for instruction following.
What about the real-world implications then? Where could this lead?
Well, the potential for deploying highly capable multitask LLMs on resource-constrained devices is huge. Think edge computing, mobile devices.
Or personalized AI assistants, handling diverse requests without needing huge models for each user.
Exactly. It also opens up possibilities for continuous learning. Imagine models acquiring new skills over time with minimal overhead without forgetting old ones.
That would be a game changer.
And just practically, the smaller storage footprint makes these adapted models easier to manage and distribute. Plus, the core idea compositional representation learning might apply beyond NLP too.
Fascinating stuff. Okay, this brings us to our novel notions segment. Based on this work, what kind of out there but maybe plausible research ideas come to mind?
Well, building directly on CSRFT, one direction could be exploring dynamic subspace discovery and merging.
Okay, dynamic discovery, what does that mean?
Imagine instead of predefining the number of skills, say K4, like in their experiment, the model could dynamically figure out it needs a new subspace when it encounters a truly novel task during training.
So it allocates new skill pockets on the fly.
Yeah. The extreme version could be a continuously learning LLM that spots distinct patterns in data and just dedicates specialized representational units to them without explicit task labels.
That sounds ambitious. What's the argument for it?
Obvious one is flexibility, right? New tasks need new representations. Dynamic allocation avoids manual partitioning.
Okay.
But maybe less obviously what happens over time. Some subspaces might become redundant or represent very similar skills. So research could look at automatically merging or pruning underutilized subspaces.
Like neural network pruning or knowledge distillation, but for these representational subspaces.
Kind of. Maintaining efficiency, preventing representational bloat.
What's the potential impact?
More flexible, adaptable AI systems that learn and evolve more organically. Probability, maybe moderate. Detecting novel patterns and managing the allocation merging is tricky.
Okay, interesting. What's your second novel notion?
The second one centers around interpretable subspace roles and router decisions.
Yeah, back to the interpretability challenge the paper mentioned.
Exactly. The idea is to really develop methods to understand what specific skill or concept is subspace, #1 actually capturing. What about #2?
Going beyond just knowing it works.
Right. The extreme goal. Tools that could visualize or explain the function of each subspace, and crucially explain why the router chose to activate a specific combination for a given input.
Why focus on this?
Well, the obvious reason is transparency. Understanding internal representations helps us grasp behavior, spot failure modes, biases, but maybe less obviously. If we can interpret the subspace roles and router logic, we might spot gaps. The model lacks a representation for X, or the router logic is flawed for Y type inputs.
Leading to more targeted improvements, or maybe even human guidance.
Potentially, yeah. Maybe drawing on ideas from representation engineering.
And the impact.
More trustworthy, controllable AI. Especially critical in high stakes areas, probability. That's a high for making progress here. Interpretability is a huge focus in ML, and CSRFT's modular structure seems like a good starting point for analysis.
Absolutely fascinating ideas. It's clear that CSRFT represents a really significant step forward in making these large language models more adaptable and efficient.
Yeah, that combination of specialized representation editing, these orthonormal subspaces, and the dynamic routing, it's a powerful way to tackle that cross-skill interference challenge.
For those of you listening who want to dive into the technical details, we'll definitely have a link to the full paper available.
And I think as we consider the implications, the big questions really circle back to scalability and interpretability, like we discussed. How do we handle vast numbers of skills efficiently? And how do we maintain our understanding of what these complex systems are actually doing internally?
Those are definitely the frontiers. It's a set of challenges that will undoubtedly drive a lot of exciting research in this field.
That's true.
Indeed. Well, thanks for joining us for this deep dive into CSRFT. We'll catch you next time right here on Talk Tensors.